Hey everybody. So I've been hinting before that there's some sort of calculus relationship between shear force, bending moment, and distributed loads. So let's talk about that here. So let's say you have some kind of beam with some supports, and it's subject to some sort of distributed load, whatever it is. Okay, and then we define this function as a loading curve. Loading curve. So I'll call it loading curve W as a function of X, and I will call this X. Okay, and then what we've talked about so far is you can draw the free body diagram of the beam, and then there's some pin over here, some roller over here, and then you can represent this distributed load as a single discrete force, where the magnitude is the area of the shape, and the location of this discrete force is at the centroid of the shape. And then once you do that, you could cut the beam somewhere, and then that exposes all the internal forces and moments. Okay, but let's say you cut the beam somewhere. I mean, for this representation, you cut the beam somewhere. Right, so then there's the distributed load. But then when you cut it, these are the reactions. When you cut it, you expose the internal forces and moments, right? The axial force, shear, bending moment, axial force, shear, bending moment. Okay, now I'll tell you the answer. The relationship between loading curve and shear is like this. Take the derivative of the shear with respect to X, and that is minus the loading curve. Okay, and there's a relationship between shear and bending moment. You take the derivative of the bending moment with respect to X, and you get shear. Okay, and then there's one more. The derivative of the axial force with respect to X is 0. So it's these three. Okay, so then maybe I'll draw them like this. So these three. You can memorize it. Well, technically, you don't need to memorize it. You could just remember there's some sort of calculus relationship between all of this, and then just look it up. Like 5 years from now, if you don't remember that there was a minus sign over here, right? As long as you remember there's some sort of calculus relationship, and then you look it up, then you say, okay, there's a minus sign here. There is not one over here. Okay, now how do we use this? It seems so simple, which it is very simple, but you still have to practice. So, till you get the hang of it. So let's try it out. Right, this is all you need. This is all you need. So try this methods. Okay, so let's take this example. Let's solve for the internal forces and moments. So first, let's figure out the reactions here. Okay, so there's a roller at A, a pin at B. There's X here and Y over here, right? So I'll decompose A and B. Okay, and then there's a load over here. And then a distributed load here. What's the loading curve? The loading curve for this particular example is a constant. Okay, but then for this, to solve for the reactions, let's represent this loading curve as just a single force here. And then the area is 80, right? So this is 80. And located at the centroid of this rectangle, which is 1 meter over here. Okay, so let's solve for these reactions. Let me move this over. Okay, so let's solve for these reactions. So in the x direction, we have bx. In the y direction, ay, by, plus 60 minus 80. I'll just bundle those together already. Okay, let's sum torque about wherever we want. How about point A? Okay, so there's torque from by, which is 2 meters. And then here to here is 4 meters. And then this one is 1 meter. Okay, so then let me point out the unknowns here. Okay, so let's solve for let's solve for bx is 0. By would be, let's see, so 80 minus 240 over 2. Okay, so then that's 80. Oh, minus 80. Which then would make AY 20 minus BY. So 20 minus negative 80 is 100. And BX was 0. Okay, so now we know the reactions. So let me just draw this again over here. So AY was 100. BY was negative 80, so this way. Okay, and then there was the distributed load here. The loading curve we know. It's a constant. And then let's not forget this load over here. Okay, now let's practice using this to solve for the shear. So dV dx equals minus W. Okay, so in the x direction, let's start from over here, like to the left of the beam. There's nothing happening, right? So it's 0. The shear is 0. But suddenly we encounter this. So imagine here's the beam and you're cutting it from this, like you cut it here. You're not cutting anything, right? Then suddenly you cut it here. Then what does it look like when you cut it here? You expose the axial force, shear, and bending moment. So notice the direction of the shear force. It's positive going up. And then take a look right here. See how this is 100 kilonewtons going up? So suddenly there's a, right, when you're cutting it over here to the left of the beam, not cutting anything, the shear is 0. Then suddenly you encounter this 100 kilonewtons in the positive direction. I just draw in a different color. So it's 0, then suddenly 100 kilonewtons in the positive direction. Okay, now what happens between point A and point B? You have this distributed load. So the shear minus W. Okay, and then that loading curve was 40. So this would be minus 40. And then solve this, right? So move dx over here. And then you can integrate both sides from x equals 0 to some other x. But definitely between 0 and 2, right? Because if you go past that over here, there's no more distributed load. So this is only valid between 0 and 2. Okay, and then this is v at 0 to some other v. So what do you have here? V minus V at 0 equals minus 40 x minus 0. So minus 40 x. And then what was V at 0? 100. So V is 100 minus 40x. Well, that's between 0 and 2. Right? So how was that usage of this calculus relationship? Not bad, right? This one. And then what does that look like? So it's at x equal to 0, it's 100. And then a slope of negative 40. When x equals 2, then it's 100 minus 80, which is 20. So then this goes down to over here, and then over here it's 20. Over here. Okay. Now, what happens at x equal to 2? Suddenly, you encounter this reaction, which is in the negative direction. So suddenly, from here, it goes down 80. This here to here is 80. Right? So if it starts at 20, then it has to go down to negative 60. Here to here. Okay, and then now what happens over here? The distributed load here is 0. Over here. Over here. So then dv dx equals, this is 0. And what does that mean? The derivative of v is 0 means v is constant. So it was negative 60, and it will continue to be negative 60 because it's constant. And then what happens here? Suddenly, you encounter this 60 kilonewton load, which is in the positive direction. So suddenly it goes up 60, like this. And it was already at negative 60, so then it goes up to 60. And then what happens over here? There's nothing over here, right? So it's 0 again. So this is shear as a function of x. Okay, how was that? Give this a try, so keep practicing. Now let's solve for the bending moment. Okay, for bending moment, it's just this one formula right here. dm dx equals v. Okay, so from here to here, I shouldn't erase what I just had. From here to here, it was 100 minus 40x. And then from here to here, it's negative 60, right? Okay, so for the bending moment, from here to here, well, it's 0 over here. And then there's no couples or anything showing up anywhere. So it's 0. Now, dm dx equals v. And from here to here, v is 100 minus 40x. Okay, so how do you solve this? Move dx over here, and then integrate both sides. From x equal 0 to some other x, but definitely between 0 and 2. Right, from here to here is just between 0 and 2. So this has to be less than 2. And then m at x equal to 0 to some other m as a function. Okay, so what do you get? And this is 0 over here. So this happens to be 0. And then 100x minus 40x squared over 2. I'll just write 20. Okay, so that's it. And this is 0, right? So that's it. What does this look like? It's a parabola. And then see the leading, this is the leading coefficient, is negative. So it's a parabola that's like this. At x equal to 0, it's 0. And then, I mean, it's not important you know how to graph things in your head, but you could do something like, what is it at x equal to 1? 100 minus 20, so 80. So it's going up. So it's definitely this side of the parabola, not this side. So it's going up like this. And then at x equal to 2, what do we have? We have 200 minus 20 times 4 is 80, so 120. So it goes up. Over here is 120. Okay, and then now the shear changes over here. So we basically have to start over, right? So try again. This time, this function over here, the shear, is negative 60. And then now we're integrating from x equal to, over here is 2, right? So from 2 to some other x, where x is now between 2 and 4, because we're over here now. Okay, so what do we have here? M minus m at x equal to 2, which was 120 kilonewton meters. And then negative 60x minus 2, right? So there we go. This is it. This is the answer. I mean, you can clean it up a little bit, but I mean, maybe I'll just leave it like this. So at x equal to 2, then this is 0. So m is 120, which is right over here. And then as x increases, it's just linear, right? And the slope is negative 60. So it's going down. And x equal to 4, then this becomes 120 minus 120, which is 0. So it's going down and then reaches 0 over here. Okay, so then that's it. Okay, so give this a try. These, right? So shear, bending moment. And then for this particular example, the axial force is just a constant. And in this example, it was 0. Okay, let me go on to a different example. I need to make sure there's a couple somewhere. So we can talk more about this part of it. Okay, so I'll see you in the next video.